All right, folks, in this section, we're going to take a look at, well, the book calls it Integration Strategies. It kind of mirrors how the chapter began. We're just going to be looking at a bunch of integrals. So in short, this section is going to be a review of all the integration techniques and tricks that you've seen so far. Everything from integrands that yield inverse trigonometric functions to U substitution, to integration by parts, trigonometric substitution, and partial fraction decomposition. All of it is fair game in this section. I can't stress enough, recognition is key. And sometimes just being legally creative is necessary. In short, you're going to have to be persistent and don't give up. Sometimes simply doing something is an important skill in order to begin the problem. So what I'm going to do is I'm going to do some of the odd exercises as examples. This is what I would do in the classroom in a face-to-face setting. After doing some of these odd exercises as examples, as usual, I'll ask you to pause the video and do a different odd numbered exercise. And, the drill. After doing that, you'll restart the video and I'll be at the board working through a solution. So without further ado, here I go, heading off to the chalkboard to do the first example. All right, folks, this section, what's kind of cool about this section is that the chapter started off, this chapter on techniques of integration, it started off with a section of a review of basic integration techniques that you would have already seen in Calc 1. And now we're at a section that, now that we've added to your arsenal, now that you've seen integration by parts, trigonometric integrals, trig substitution, partial fractions, this is like another review type section. So the way I will handle this, it's the way I would handle it in a traditional face-to-face class, is I will just do some odd problems and then I'll ask you to do some problems. So for example, if we were in a classroom, I would say let's do number 9 right now and we'd do it together, and then after doing number 9 I would ask you, like I tend to do a problem from the homework, and that's how this section is going to go. So first one here, number 9. Integrate from 4 to 6, 1 over the square root of 8x minus x squared. Alright, so I can tell you honestly, the first thing I would look at is a u substitution, letting u equal what's under the radical. But I see that du would be an 8 minus 2x dx, and that's not going to work. That u sub isn't going to work. Next, I look at what's under the radical, and I'm wondering, well, what happens if I complete the square on what's under the radical? So let me pull what's under the radical. Let me pull that over here. It's an 8x minus x squared. And let me go through the process of trying to complete the square on this mess. The first thing I would do is I would rewrite it as negative x squared plus 8x. And then because, that's a problem, I would factor out a negative 1, so I have an x squared minus 8x. Okay, now I look and I say to myself, what would I have to have appear inside the parentheses here? What number would have to appear so that I would have a perfect square that could be factored? Well, the process of completing the square to determine that number is you take half of this number and then square it. Well, half of negative 8 is 4. Half of negative 8 is negative 4. Negative 4 squared is 16. So I have to add 16 in there. So let me, let me go ahead and add in the 16. But I have to preserve the overall value here. I can't just arbitrarily add a 16. I have to do something else. So now keep in mind, if I add a 16 in here, there's a negative sign out front. If I were to distribute that negative, that would give me a negative 16. So to preserve the fact that all of this has to still equal this, I need to add a 16th. And you should be able to see that what I've written down right now is the exact same thing as this, it's the exact same thing as this. And that's what I mean by when we complete the square, we have to preserve the original value. So if I now rewrite this in a more aesthetically pleasing form, that would be a 16 minus that quantity. And I might as well go ahead and factor this. This factors to an x minus 4 quantity squared. So, my original integral, what I now have under the radical is a 16 minus the quantity x minus 4 squared. So to me, this looks like an integral that's going to result in inverse sine. It has that form of inverse sine. You know, a is 4. U is x minus 4. So du is dx. So I don't have to worry about putting in any extra multiplier. So we see it does have the form of 1 over the square root of a squared minus u squared. So the antiderivative is inverse sine. This antiderivative is simply inverse sine of u over a. So that's, well, u is x minus 4 over a, which is 4. And now I need to evaluate that from 4 to 6. So let's see, 6 comes in for the x, 6 minus 4 is 2, 2/4 is 1/2. So it's inverse sine of 1/2 minus inverse sine of, when 4 comes in, oh, well, we get 0. So it just is a basic trig problem now, basics of unit circle. Inverse sine of 1/2, that's pi over 6. Inverse sine of 0 is 0. So that's it for number 9. So here's what I want you to do now. Pause the video, go to the exercises, and do number 11. After you've done number 11, I'll be here at the board working through it, and we'll make sure you have it correct. All right, number 11, you were asked to integrate from 0 to pi over 4 the quantity secant x minus cosine x squared, dx. Okay, I would begin this one by, well, foiling out that integrand, doing secant x minus cosine x times secant x minus cosine x. So here we go. When I do secant x minus cosine x times secant x minus cosine x, I'm going to get a secant squared x minus 2 secant x cosine x plus cosine squared x. Next, since secant is the reciprocal of cosine, secant is 1 over cosine, secant x times cosine x is just 1. So I would rewrite this as secant squared x minus, well, 2 times 1 is 2, plus cosine squared x dx. All right, I'm starting to see some progress here. I know what the antiderivative of secant squared is. That's easy. Antiderivative of secant squared x is just tangent x. I know the antiderivative of 2 is 2x. Antiderivative of cosine squared x, we need to use the power reducing identity. So let's write down the power reducing identity. Cosine squared is 1/2 1 plus cosine 2x. And let me pull this up here. And as I pull the problem up here, I'm going to go ahead and distribute the 1/2 Okay, now I just take care of some like terms, and the only like terms here are negative 2 plus 1/2. So we know negative 2 plus 1/2, negative 2 plus 1/2 is negative 3/2. And now we get our antiderivative. As we said, the antiderivative of secant squared, well, that's tangent x. The antiderivative of negative 3/2, that's just negative 3/2 x. And the antiderivative of 1/2 cosine 2x, well, that's 1/4 sine 2x. And now we evaluate that from 0 to pi over 4. So let's see. Tangent of pi over 4. Tangent of pi over 4 is 1. Minus 3/2 times pi over 4. Well, that's a 3 pi over 8. Plus 2 times pi over 4. 2 times pi over 4 is pi over 2, and the sine of pi over 2 is 1. So 1 times 1/4 is 1. Minus, now when 0 comes in, tangent of 0 is 0. 3 times 0 is 0. Sine of 0 is 0. Oh, that's kind of nice. So it looks like we have, 1 plus 1/4. So that's a 5/4 minus 3 pi over 8. And I'll just leave it as that. So hopefully you got that for number 11. I'll be right back to see the next odd number exercise we're going to do as an example. All right, the next one I thought we'd do as an example is number 17. This is integrating from 1 to 2, w cubed e to the w squared dw. Okay, as I've said, several times, and I'm going to say it again, sometimes you have to be creative, legally creative when attacking an integration problem. It's like a little puzzle you have to figure out. I've also said it's not possible to show you every single type of creativity or trick. And this is an example of one of those. So I'm going to start off by rewriting this. I'm going to rewrite the w cubed. Let me rewrite it as w times w squared. Okay, here's why I want to do that. If I let x equal w squared, then dx is 2w dw, or 1/2 dx is w dw. So when I substitute in, alright, so there's an x, here's an x, so that gives me x e to the x, and this w dw is replaced with 1/2 dx. So I put the 1/2 out front. And if you're wondering why, here at this step, why didn't I just do a u substitution? Why did I pick x? And that's the reason why I picked an x is because to attack this integral, I'm going to use integration by parts. So here we go, integration by parts. And with integration by parts, I'll let u equal x. dv is e to the x dx. du is dx. v is e to the x. So let me pull it up here now. So we have 1/2. And now I'm going to crank it through, this integral through integration by parts. So remember, integration by parts is u times v. So that's x e to the x minus the integral of v du, which The antiderivative of e to the x is e to the x. That wasn't too bad. Now I resubstitute for my x. X is w squared. So I have 1/2 w squared e to the w squared minus e to the w squared. And that allows me to now bring back the original limits of integration. Remember, those limits of integration are for the variable w. And those limits are 1 to 2. So we would get, oh boy. See, 2 comes in for the w. So we'd have 4e to the 4th minus e to the 4th. That's not too bad. Minus 1/2. 1 comes in. Oh, so we just get an e minus e. That's not too bad. We know e minus e is 0, so this is all 0. So what do we have here? Nothing more than 1/2. If I do that subtraction, I get 3e to the 4th. So we get 3/2 e to the 4th. That's the value of that definite integral. All right, so let's see. I want you to do one right now. The one I want you to do in your exercises is number 21. So you know the drill. Pause the video, do number 21. When you're done, restart the video. I'll be here at the board working through it. All right, 29, you're asked to integrate x to the 9th, natural log 3x dx. I really don't see anything fancy here. I just see this as straightforward integration by parts, where you let u equal the natural log of 3x, dv is x to the 9th, dx, du is 1 over 3x times the 3 dx, v is 1/10 x to the 10th. So my integral x to the 9th, natural log 3x dx, when I crank it through integration by parts, I get u times v, so that's a 1/10 x to the 10th, natural log 3x, minus the integral of v du. Well, first thing I'm going to notice is here in my du, the 1 over 3x times 3, this would simplify to 1 over x. So v is 1/10 x to the 10th, du is a 1 over x dx, so I'll rip this 1/10 out front. So I'd have x to the 10th times 1 over x. Well, x to the 10th times 1 over x, that would simplify to x to the 9th dx. And that's a pretty friendly integral to take care of. The antiderivative is 1/10 x to the 10th, so 1/10 times 1/10 is 1 over 100, x to the 10th plus c. That's all there was to number 21. So give me a moment and I'll be right back to see the next odd number exercise that we will do as an example. All right, the next one I thought we would do as an example is number 23, where we're going to integrate sine x over cosine squared x plus cosine x dx. I really like 23. I like it for the same reason that I liked the last example that I did, which was number 17. The reason why I like these is, like, if you think back to number 17, in number 17 we kind of had to do two different things. We did a substitution, and then we followed that up with an integration by parts. This is going to be in the same manner. We're going to do two different things, two different techniques. So the first technique, the first thing I would think of doing here is a u sub. Let u equal cosine x. Then you know du is a negative sine x dx, or negative du is sine x dx. And I'd substitute in. My denominator is u squared plus u, and that's what I get after the u sub. Now this looks an awful lot like something that I could crank through partial fraction decomposition. So let me pull this over to the side. Let's take it through the process of partial fractions. 1 over, well, let me go ahead and factor the denominator. That's u times u plus 1. Process of partial fractions, you'd have an a over u plus a b over u plus 1. You know, multiply both sides by the LCD to get 1 equals a times u plus 1 plus b times u. You pick convenient values for u. Here I would pick -1. So if I let u equal -1, let's see, I get 1 equals, this is gone, so we'd have b times -1. That's a negative b. So that tells me b is -1. That tells me the next convenient value to use for u is 0. So let's see if u is 0. Oh, I still have a 1 equals a. Oh, and that's, oh, look at that. We immediately know a is 1. So that's not too bad. So that means I can rewrite this. I can now rewrite it as a over u. So that's 1 over u plus b over u. So plus -1 over u plus 1. I'll write that as -1 over u plus 1. Very, very friendly to get an antiderivative here. We know the antiderivative of 1 over u is natural log absolute value of u. The antiderivative of 1 over u plus 1, we know that's the natural log absolute value of u plus 1. And then we, resubstitute. So we have the natural log absolute value of cosine x minus the natural log absolute value of cosine x plus 1. Or if you wanted to, I guess you could, distribute the negative to get negative natural log absolute value of cosine x plus the natural log absolute value of cosine x plus 1. Or you could rewrite it as the natural log absolute value of cosine x plus 1 minus natural log absolute value of cosine x, which I'm sure then the back of the book would have it as the natural log of absolute value cosine x plus 1 over cosine x. They would use a property of logarithms. But 23 is very similar to what 17 was. We used two different techniques in doing the integral. All right, here's what I'd like you to do right now. Go into the exercises. Pause the video, go into the exercises, do number 29. After you've done number 29, restart the video, and I'll be here at the board working through it. Okay, number 29, you were asked to integrate 2 cosine x plus cotangent x all over 1 plus sine x dx. Okay, I look at this and the first thing that pops into my head is this trig function almost seems like an outlier. I mean, I see a cosine, I see a sine, I see a cotangent. So maybe the first thing I would try is to rewrite cotangent in terms of sines and cosines, just to see what happens. So we know cotangent can be rewritten as cosine x over sine x. All right, now I don't really like the way this looks. I have a fraction. And in the numerator of my fraction, I have a fraction, so I'm not a big fan of fractions to begin with. So what I would do next is I would multiply the numerator and the denominator by sine x. And look what that gives us. It gives us a 2 sine x cosine x plus a cosine x all over a sine x plus sine squared x. I'm going to try a basic u sub. I see something here. I mean, what I'm visualizing is if I let u equal the denominator, I know the derivative of sine x is cosine x. I see a cosine x here. Plus, and then when I differentiate sine squared x, well, that derivative is 2 sine x, and then the chain rule gives a cosine x. So if I let u equal the denominator, du is cosine x plus 2 sine x cosine x dx. This ends up being very friendly. It's just u sub gives me this, which we know that antiderivative is natural log absolute value of u plus c, which we know is the natural log absolute value of sine x plus sine squared x plus c. Hey, that one wasn't too bad at all. So give me a minute and I'll be back with the next example we're going to look at. Alright, this next one is just an example, but actually it's going to be very important for number 57. Where I thought we would just integrate sine square root x over square root x dx. So I look at this and I immediately think, well, a basic u sub, if u is square root x, du is 1 over 2 square root x dx, or 2 du is 1 over square root x dx. So when I substitute in, I have sine of u. The 1 over square root x dx is 2 du. So I rip the 2 out front. I get an antiderivative of sine. U is negative cosine u. Resubstitute. That one wasn't too bad. And here's why I said this was really kind of setting us up for number 57. Which I'm going to want you to do number 57 after I write it on the board and talk about it a little bit. 57, you're asked to integrate the sine of square root x dx. So there's a trick here. The trick is to rewrite that integrand so that we would see this. Because we know what the antiderivative is for sine square root x over square root x. We know that antiderivative. So the trick would be to come in here and multiply by square root x over square root x. So that you would see that. And maybe integration by parts would be the next thing to do. So here's what I want you to do. I want you to pause the video. I want you to do number 57. Once you've done number 57, restart the video. I'll be here at the board working through it. Alright, number 57. You're asked to integrate sine square root x. Gave you the hint to rewrite it like this. And remember from the prior example, we learned that the integral sine square root x over square root x is negative 2 cosine square root x plus c. And then I gave you one final bit, one little more hint was this looks like it should be cranked through integration by parts. I mean, if I let u equal square root x and dv equal the sine square root x over square root x dx, well, we know du, here we know du is 1 over 2 square root x dx. We also know what v is. We've already done it. So we know v is negative 2 cosine square root x plus c. Oh, I'm not even going to put the plus c on. Integration by parts, I'll save the plus c for later. So I can now crank this through integration by parts. It's u times v, so that's a negative 2 square root x cosine square root x minus the integral of v du. Well, when v du goes in, notice 2 and the 1/2, that would cancel out. I'd rip the negative out front to make this plus. So I have cosine square root x over square root x dx. So I need to knock out this little integral right here. Well, let me just kind of pull it over here. I mean, I think you should see how we're going to attack that integral. I mean, it looked an awful lot like that last example we did where we did a basic u sub, where we let u equal square root x, du is 1 over 2 square root x dx, or 2 du is 1 over square root x dx. So we substitute in, we have cosine u du, 2 out front, antiderivative is 2 sine u, 2 the sine of square root x. So we just did this. So this integral, the integral sine square root x, is equal to, that's the antiderivative, negative 2 square root x cosine x, oh, I left off the square root, negative 2 square root x cosine square root x plus 2 sine square root x plus c. So here's the deal. This is what you originally started with. So really what was embedded in this was first doing the trick of multiplying it by square root x over square root x. And then this integration by parts, you know, this we integrated in the prior example. So again, creativity. You stick with it. But give me a minute and we'll see what the next example that we're going to look at is. All right, I thought the next one we would do as an example is number 59. 59, you're being asked to integrate 1 over x to the 4th plus x squared dx. And I would probably start this one off, oh, you know, I could factor that denominator. And that might initially take me down the path of partial fractions. I'm going to tell you why I'm not going to do partial fractions. In fact, I'll come over to the side here and set up what the partial fractions would look like. You have an a over x plus a b over x squared plus a cx plus d over x squared plus 1. And if I multiply both sides by the LCD, I would get a 1 equals ax times x squared plus 1 plus b times x squared plus 1 plus cx plus d times x squared. And right now is when I'd say I don't want to go any further with partial fractions because I only have one convenient value of x. X equals 0. That's the only convenient value. X equals 0 would tell me that b is 1. But I still have to get a, c, and d. There are no more convenient values for x. So I'd have to pick 3 different values for x to come up with 3 equations involving a, c, and d. I would have to then remember algebra in solving a system of 3 equations with 3 variables, which means I would have to go through a very long process of the elimination method. It's just sounding like a big, long algebra nightmare. So I thought partial fractions, but now I'm having a rethink. And here's the rethink I'm having. What if I let x equal tangent theta? I mean, if x is tangent theta, we know dx, well, the derivative of tangent, is secant squared theta d theta. So when I substitute in, well, that would be a tangent squared. This would be tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared. And dx is secant squared. Wasn't that nice? The secant squareds cancel out, which leaves us with a 1 over tangent squared. We know 1 over tangent squared is cotangent squared. And we know that cotangent squared is, thanks to a Pythagorean identity, cosecant squared theta minus 1. I'm going to have to pull this up here now. Think about how friendly this is. The antiderivative of cosecant squared. We should know that straight away. It's negative cotangent. And the antiderivative of 1, that's just theta. Okay, but now we have to get out of the theta world and get back into the x world. So we know that means right triangle time. Let's see, I substituted tangent theta is equal to x. So if tangent theta is equal to x, cotangent theta is the reciprocal. So it's just 1 over x. And if tangent theta is equal to x, that tells me theta is inverse tangent of x. Looks like I'm done. This is negative 1 over x minus theta is inverse tangent of x. That is a lot more efficient and a lot quicker than if I had gone through partial fractions. So let me write down the next example that we're going to look at. So I'll be right back, and we have another example that we're going to do. All right, the next example I thought we would do is number 65 in your book. It's integrating from 0 to 1 over 6. The integral 1 over square root 1 minus 9x squared dx. Now this just looks pretty straightforward. It looks pretty quick. It looks like a straightforward inverse sine. You know, a is 1, u is 3x. To get a 9x squared here, it has to be a 3x quantity being squared. So u is a 3x, which means du is a 3dx, or a 1/3 du is dx. So I do have to worry about this 1/3, but I can get this antiderivative straight away. We know the antiderivative of inverse sine. We know the derivative that involves inverse sine. It would be inverse sine of u over a, which is just the 3x, but I have to remember this 1/3 would also be playing the game. So that's it. That's the antiderivative. Now we just need to evaluate it from 0 to 1/6. So 1/6 comes in first, and what do we get? 1/3 inverse sine of, that's inverse sine of 1/2 minus 1/3 inverse sine of 0. Inverse sine of 1/2, that's pi over 6. 1/3 times pi over 6 is pi over 18. Inverse sine of 0 is 0. So that's it for 65. It's just pi over 18. Now I want you to do two. I want you to do 66 and 67, which are going to be very similar looking to number 65. So pause the video, do number 66 and 67. Once you've done them, restart the video, and I'll be here at the chalkboard working through them. All right, in 66 you were asked to integrate x over the square root 1 minus 9x squared dx. Looks very similar to number 65. You know, 65, the integrand was basically the same, except there was a 1 up there in the numerator. So hopefully that you're seeing this recognition, kind of coming back to recognition again. 65, we recognized it would involve inverse sine. 66, I hope we recognized that this was a basic u sub. U is 1 minus 9x squared du, negative 18x dx, negative 1/18 du is x dx. So we substitute in, got a negative 1/18. We'd have 1 over the square root of u, so that's u to the negative 1/2. Get an antiderivative. Negative 1/9 u to the 1/2. So I'll write that as square root 1 minus 9x squared. '67. Hopefully we recognize in 67 that this is a pretty classic, straightforward trig sub. I mean, I see 9x squared, I see that as being the quantity 3x squared. So I would let 3x equal sine theta. And keep in mind, if 3x is sine theta, that means x is 1/3 sine theta. Dx is 1/3 cosine theta d theta. So when I substitute in, x squared, so that'd be a 1/3 sine theta, all of that being squared, so that's a 1/9 sine squared theta. The 1 minus 9x squared, well, that would be 1 minus sine squared, which is cosine. So that radical will just become cosine theta. The dx is 1/3 cosine theta, d theta. So the cosine thetas cancel out. The 1/3 times 1/9 is 1/27. Let me go ahead and rip that out front of the integral. And you're just left with the sine squared theta d theta, which hopefully you're saying, I know how to attack that, use the power reducing identity. This is 1/2 quantity 1 minus cosine 2 theta. Rip the 1/2 out front. So you have 1/54th, the integral, 1 minus cosine 2 theta. Get your antiderivative. So it's theta minus, see the antiderivative of cosine 2 theta is 1/2 sine 2 theta. And, you know, just kind of looking ahead, sine 2 theta is 2 sine theta cosine theta, so 1/2 times 2 is 1. Trig sub, so I come over here and I get my right triangle. And let's see, we did 3x is sine theta. So sine is opposite over hypotenuse. Oh, the missing side, square root 1 minus 9x squared. We need to know what theta is. Well, if sine theta is 3x, theta is the inverse sine of 3x. We know sine theta. Cosine theta, well, from the right triangle we have cosine theta is adjacent over hypotenuse. So I get a 1/54th theta, which is inverse sine of 3x minus sine theta cosine theta. Plus c. So hopefully you got 66, hopefully you got 67, hopefully you looked at 65, 66, and 67 together as 3 consecutive exercises where the theme is recognition, recognition, recognition. So that's it. We've done a lot of examples and a lot of your odd-numbered exercises. So do the rest of the assigned exercises in this section. That's all for the video. Thanks for watching.